Have you ever wondered if the fundamental rules of the universe are actually constant? I mean, what if they're more like guidelines, things that can bend or even completely change under enough pressure? Well, today, we're going on a trip to the most extreme places in the cosmos to find out what happens when physics gets pushed to its absolute breaking point. And when I say extreme, I mean it. We're talking about conditions so intense they make a supernova look like a little sparkler. We're going to visit the universe just moments after the Big Bang, this incredible plasma billions of degrees hot, and then dive into the hearts of stars where matter is squeezed so tight it almost ceases to be matter. So in these cosmic cauldrons, do the particles that we know and love, the building blocks of everything, do they still play by the same rulebook they follow here on Earth? That is the big question we're going to try and answer. So here's how we'll break it down. First, we'll meet a family of particles called leptons. Then we're going to learn about this weird thing they have called an inner compass. After that, we'll see what happens when you put them under some serious cosmic pressure. Check out the surprising results, and finally, figure out why all of this is so important for decoding the universe. Okay, first things first. Let's meet our cast of characters. They're a family of fundamental particles, and they're called the leptons. Now, think of this family as being split into two teams. On one side, we've got team charged. This is where you'll find the good old electron and its two much heavier cousins, the muon and the tau. On the other side, we have team neutral. These are their kind of ghostly partners, the three types of neutrinos. And trust me, this rivalry between team charged and team neutral is the key to this whole story. All right, so every single one of these particles has this kind of hidden property, almost like an internal compass. And in the world of physics, we have a name for that. It's called its magnetic moment. So what does that actually mean? Well, think about it like this. If you tossed a bunch of compasses into a magnetic field, they'd all snap to attention and point in the same direction, right? Particles with a magnetic moment do the exact same thing. It's really just a fundamental way of measuring how much they react to magnetism. Now, under normal, everyday conditions, like in the vacuum of space, our two teams follow completely opposite rules. For team charged, it's simple. The heavier the particle, the weaker its inner compass gets. But for team neutral, the neutrinos, it's the total opposite. Their magnetic moment is what we call induced. It's sort of a secondary effect. And for them, the heavier they are, the stronger their compass becomes. This opposing relationship is absolutely crucial, so keep it in mind. So, okay, those are the rules when everything's calm. But we're not interested in calm. We're heading back into those extreme environments. So let's turn up the heat in our cosmic cauldrons and see what happens. See, when you drop a particle into a super hot, super dense soup, it's not alone anymore. It is constantly bumping into and interacting with this whole sea of other particles around it. And all of those interactions, they kind of bog it down. It makes the particle behave as if it's heavier than it really is. Physicists have a cool name for this. They call it an effective mass. And that brings us right to the heart of this research. If particles on both teams are getting heavier because of this crazy environment, what happens to their inner compasses? Do they still stick to those opposite rules we just talked about? Well, let's start with team charged. And for them, the answer is, yep, the old rule holds up just fine. As that hot, dense environment adds effective mass to the electrons, muons, and taus, their little inner compass just gets weaker and weaker. The relationship is still totally predictable. Their magnetic moment is just inversely proportional to their mass. As one goes up, the other goes down. Simple. But now we get to team neutral, the neutrinos. And because their starting rule was the complete opposite, their outcome in this extreme environment is also the complete opposite. As they gain that effective mass from all those interactions, their inner compass actually gets stronger. So for neutrinos, the magnetic moment is directly proportional to mass. More effective mass means a stronger compass. It's this really beautiful opposing symmetry between the two teams that makes this such a fascinating discovery. Okay, so that's the theory, but talk is cheap, right? Let's actually look at the data from the research. Think of this as the official scoreboard that shows us exactly how these particles are behaving under pressure. So here's the chart for team charged. Just look at that last column, thermal contribution. See how all the numbers are negative? That's the proof right there. The environment is reducing their magnetic moment. And notice how the biggest effect is on the lightweight electron, and it gets way, way smaller for the heavier guys. The rule works perfectly. And this graph just makes it crystal clear. As the temperature on the bottom axis goes up, just look at that solid line for the electron. Its magnetic moment absolutely takes a nosedive. The other two lines, for the heavier particles, they're practically flat by comparison. It's exactly what the theory predicted. Okay, now for Team Neutral's scoreboard. Check out that last column. This time, all the numbers are positive. That means the environment is boosting their magnetic moment. And what's really important is that the heaviest of the three, the tau neutrino, gets the biggest boost of them all. And here's the graph to prove it. As the temperature rises, the magnetic moments for all three neutrinos climb up. But look at that dashed line for the heavyweight tau neutrino. It just shoots up way more dramatically than the others. Again, the rule holds perfectly. It's the exact opposite of what we saw with Team Charged. So we've seen how these tiny little particles act in these absolutely insane environments. But what's the big picture here? Why does any of this matter? I mean, who cares about the strength of a particle's inner compass? Well, here's the bottom line. What we've learned is that these fundamental properties we thought were set in stone, they're not. They change depending on their surroundings. And we've now seen for a fact that Team Charged and Team Neutral react to this cosmic pressure in completely opposite ways. And understanding that, well, it's absolutely essential if we want to build accurate models of how stars live and die, and how our entire universe came to be. And hey, don't just take my word for it. The researchers themselves say that getting a detailed handle on this behavior is probably going to resolve some of the biggest unsolved mysteries of the universe. So this isn't just some weird particle quirk. It's a genuine clue to understanding, well, everything. It really makes you wonder, doesn't it? If something we thought was so fundamental, like a particle's magnetic moment, can be so dramatically twisted and changed by its environment, what other bedrock rules of physics might start to bend or maybe even break when you really turn the universe's dial all the way up to 11?